Data scientists in regulated industries face a trade-off between transparency and predictive performance. Traditional GLMs are transparent and regulatory compliant, but they're labor-intensive and limited in capturing complexity. Modern machine learning, on the other hand, delivers superior predictions automatically, but as black box models, they're difficult to get approved by regulators. Avenue solves this problem with a novel method of converting gradient boosting machines directly into transparent factor tables. I'll demonstrate with a real example here in this Jupyter notebook. So here we're just going to load in the abalone dataset from scikit-learn. This dataset contains features related to the physical dimensions and weight of an abalone shell, and you are meant to predict the age of the abalone from them. It's a difficult problem for standard regression techniques because there are nonlinearities as well as many collinearities between these features. The features are all correlated, and it's difficult for the modeler to figure out which features to include, which not to include, and how to parameterize them. Modern machine learning, like this benchmark random forest model, don't struggle with this at all. Here's where we tune our Avenue model. Avenue is based off of light GBM, and so these parameters probably look familiar to anyone who's familiar with light GBM, but we're not doing standard parameter tuning. Instead, we are doing a multi-objective parameter tuning where we are trying to minimize the complexity of the model along with the cross-validation score. So instead of giving one optimal model, we actually are given a set of models along a Pareto frontier, and we can choose anywhere along this frontier of the model that fits our use case best. If we purely want the best predictive performance without regard to how interpretable it is, we can just choose a model over here or just use the standard light GBM package. But if we want to increase our interpretability, we can select a less complex model without giving up hardly anything on the cross-validation score. For this example, we will just select this model here, and we can fit it with a single line of code, and we'll just scroll down to compare the results to our random forest. So here we see that the random forest mean squared error on the test set is 4.712, and the light GBM is, and the resultant table model that Avenue extracts from that light GBM has the mean squared error of just slightly better, about the same, of a 4.71. You notice that the mean squared error between the light GBM and the table model are exactly the same, and that's because the predictions are exactly the same. It's the same exact model. It's just expressed in a transparent way, and that is the novelty that Avenue is bringing. We can look at an example of what these tables look like. If you're familiar with the insurance rating in the industry, they work the same way. You have just a set of factor tables. Each table here is just a lookup table. So each row here is a group, and these are upper bounds to the group. So if you have a shell weight of 0.05, for example, you would find yourself in this group here. You would grab this rating factor and you would sum it to the lookups from all the other tables. The result is, basically what you would get out of a generalized linear model, but it's done automatically with light GBM, and the predictive power is matching or exceeding that of other black box machine learning models. Here is a plot that many practitioners in the insurance world will be familiar with. You have the weights as bars, and you have the one-way prediction, which is just the group average prediction, and then you have the rating factor all plotted together. And you can see that the rating factor for the shell weight feature, we've found many nonlinearities. Let me just look at height, for example. Here you can see that we've handled the collinearity very well as well. This height variable is highly correlated with shell weight, but instead of tracking very closely to the one way, we are now flattening out the predictions. Or this is the rating factor, and so we are not like double counting. We have light GBM has produced a model that's handled the collinearities well, it's handled the nonlinearities well, and it's also giving interaction tables as well. Here is the sex variable, the 0, 1, and the -999 being all other, interacted with height. And you can see we are not overfitting this. Not all of these category combinations even have a non-zero factor. The regularization that's inherent in the light GBM underlying model takes care of that. So the result is we get a model that's essentially done. It's handled nonlinearities well. It's handled interactions. It's handled collinearities. It has also performed feature selection for us. So we end up with a great model that's ready to use out of the box. It's fully transparent. You can trace each prediction through the tables, looking at the rating factors. You know exactly how each prediction is formed. What's the end result? Well, we get massive time savings. What used to take actuaries and data scientists weeks of model development time looking for features, feature interactions, nonlinearities, it can all be done in minutes. We just ran one tuning function, and then we chose which model we wanted, and we fit that in just a few seconds. If this demonstration has piqued your interest and you want to learn more, contact us today at info@avenueanalytics.com.